Hello everyone! This video is entitled Emission and Absorption Spectra. In this video, I will explain how emission and absorption spectra work, how they can be used to identify elements, and why these analytical methods of spectroscopy are utilized. I will also make clear how these concepts are related to the notion of a quantum and the study of quantum mechanics. If you have not yet watched my video on electromagnetic radiation, it is recommended that you do so first to fully understand this material. You can find a link to that video in the description below. Okay, let's get started.
The emission spectrum of a chemical element or chemical compound is the spectrum of frequencies of electromagnetic radiation emitted due to an atom's electrons making a transition from high energy state to low energy state. I know, that sounds very confusing. To you, it's probably just a bunch of words. So let me show you what this means with this little pop-up here, okay? So this image has two Bohr-Rutherford diagrams in them. The one at the top is essentially showing an electron being hit with a certain amount of energy. And that energy is going to be absorbed by that electron, and it's going to jump from the first orbital ring to the second orbital ring, okay? In the diagram below it, that same electron that absorbed the energy is now releasing that energy. And as it releases the energy, it falls from the high energy state now to a low energy state. We call the low energy state ground state, and we call the high energy state an excited state. So in the diagram at the top, a ground state electron absorbs energy and jumps to an excited state. In the diagram in the bottom, you have an excited state electron releasing energy, and it falls down back to its ground state. Okay, let's go back to the slide. Before we go any further, it's important to note that the energy an electron is releasing when it falls from excited state back down to its ground state is in the form of light. It's a photon. What's more is the photons that these electrons are releasing when they fall from excited state to ground state are within the visible spectrum. They have frequencies that we can see. So an emission spectrum consists of distinct colored lines that are discontinuous, i.e. it's not a rainbow. So if you look at the bottom here, we have the emission spectrum for hydrogen. So you see all these distinct colored lines. Each one of those colored lines represents a photon that was released from a particular electron. The reason why you have so many different colored lines, and they're different specific colors, is because each electron can jump different amounts of energy levels. So if I have an electron that jumps 3 energy levels, it's going to release a photon with more energy than an electron that jumped 1 energy level. And the different colors represents the specific energies of each one of those electrons. Okay, so let me clarify this. Let's jump to another pop-up here. Okay, this is the visible spectrum. Okay, now I want you to note on the left side of this picture, you see that it says radio waves at the top and gamma rays at the bottom, which means that the energy increases going down, okay? Now, you can see that there's a 700 nanometer wavelength for red and a 400 nanometer wavelength for blue, okay? Remember, the larger the number, the lower the energy, because the larger the number, that means that you have a larger wavelength, which means you have a lower frequency, which means you have a lower energy. If you have a smaller wavelength, like blue here, that means that you have a smaller wavelength, but a higher frequency, which means you have higher energy. And that's why it's going down towards the gamma, okay? So if I have, for instance, an electron that jumped many energy levels, I might see a colored line in the blue spectrum, or maybe even the purple spectrum, which actually comes right after blue. You don't see it here, but it comes right after blue. If I have a lower energy jump, so let's say it's just 2 or 3 energy levels, I might see something in the middle, maybe with the turquoise or the green or the yellow. But if I have a very low energy jump, so I have an electron that only jumped one energy level, okay, I might see a colored line in the red spectrum or maybe in the orange spectrum, depending on the element. So let's go back to the slide. Now, some of you guys might be looking at the hydrogen emission spectrum with a little bit of confusion. You might be wondering, how is it possible that the hydrogen emission spectrum has 5 distinct colored lines, each line representing the specific amount of energy that an electron released when it fell from excited state to ground state, but hydrogen only has one electron? The reason why this happens is because when we do experiments, we're not doing experiments on one specific hydrogen atom. No, we're doing it on a cloud of hydrogen. So let's say I shoot a cloud of hydrogen with energy. One atom of hydrogen might absorb a certain amount of energy that causes its electron to jump one energy level. When that electron jumps from its ground state up one energy level, as it falls, it's going to release a photon within the red spectrum. So you can see that red line there. Whereas another hydrogen atom might absorb much more energy, and it might cause that electron to jump quite a few energy levels, let's say 4 energy levels. When that electron falls from its excited state, it's going to release a photon within the violet range. So you can see those violet ranges there. Maybe 4 energy levels represents one of those lines, and 3 energy levels represents a different one of those lines, maybe the blue or the turquoise. And the special thing about hydrogen is each one of those hydrogen atoms can only get excited to a specific point. So specifically to those lines. You're not going to see lines outside of those 5, which is why we look at these spectrums as fingerprints for elements. This image here has 4 Bohr-Rutherford diagrams. Each one of them is showing an electron falling from a specific energy level down to its ground state. And each of those falls represents a different amount of energy that's being released, and hence a different color. So if you look at the one on the far left, the violet there, you can see an electron is falling 4 energy levels, from energy level 6 back down to energy level 2. And that energy drop is releasing that nice purple color. If you look all the way to the right, the red color, you can see that an electron is only falling 1 energy level, from 3 to 2. And that's why the photon is in the lower color spectrum. It's in the red spectrum. And of course, you have the middle colors, blue and green, because of the variance in their fall. So 5 to 2, and respectively 4 to 2. Okay, let's go back to the slide. Different types of matter emit unique line spectra. So like I said before, the hydrogen emission spectra you see at the bottom here is actually used as a fingerprint for hydrogen. It's used as an identifier. And the reason why that is because hydrogen is the only element that will create those specific colors in those specific regions on a detector. So a different element, for instance, will create specific colors of its own in specific areas on a detector, and that allows us to identify that matter as what it is. So we use these spectra to identify differences in matter. We use it to identify matter. These spectrums provide information about the arrangement of electrons in an atom. So we're not going to focus too much on that topic in this package, but it becomes critical for our understanding of the packages to come. So you have to understand, ultimately, we're moving towards the arrangement of electrons. We're moving towards the understanding of how electrons are arranged in an atom and how we get to that understanding from spectra. So you need to fully grasp this topic to grasp the topics that are coming. Again, I'm using this information to scaffold to the ideas that we ultimately need to reach. So that second point becomes very important in the future. Now, the points that are coming in the slide are essentially review points of what we've already discussed. So it's nothing new, just a review, a refresher of what we just finished discussing. So emission bright line spectra. So it's oftentimes referred to as a bright line spectra because you can see that on the black detector at the bottom here, you can see that there's bright colored lines. And so the emission line spectra, also known as the emission bright line spectra or the bright line spectrum, okay? This type of spectrum can be produced when high voltage is applied to a gas. And so there's a diagram on the slide to come. We'll get to that and I'll fully walk you through that. The electrons in the gas atoms will absorb the energy, okay? And the electrons, when they absorb these energies and get to a high excited state, they then fall to a lower energy state or their ground state. And when they do that, they emit particular frequencies of light that will hit a detector on the opposite side and create these bright line spectrums. The energy or radiation released appears as bright lines on the spectrum. Different gases will emit different frequencies of light when energized, okay? So let's jump to that diagram, and here it is. So I'm going to draw your attention to the center of this diagram, the gas discharge tube containing hydrogen. So I'm just going to highlight that for you right there, okay? So in this tube, we have hydrogen. And what we're doing at either end of the tube is we're basically just pumping really high voltage energy into the tube. What that energy is doing is it's exciting the electrons in the hydrogen atoms and causing them to jump from low energy state to high energy state. When those electrons fall from the excited state to ground state, they're releasing their photons, their colored beams. But because all of those colored beams are being released at the same time, we, with our human eyes, cannot differentiate between the different colors. To us, it comes out as one just white beam of light. And so we take that beam of light and we filter it by passing it through these slits to create really just a funneled beam to pass through a prism. That beam is passed through a prism, and the prism splits it into the various different colors of that specific element. In this case, it would be hydrogen. And so those colors hit a detector, and we get our spectrum, okay? And so that's how we essentially create these emission spectrum or bright line spectrums for elements. Now, if the element can't be gaseous at room temperature, what we do is we actually burn that element. So it is possible. All you really have to do is add a lot of energy to an element and cause it to emit light, okay? So the next thing we're going to talk about is the absorption dark line spectrum. It's actually the exact opposite of the bright line spectrum, where the emission spectra, we're essentially measuring the light that is released by excited electrons. In the absorption spectra, what we're doing is we're measuring the energy that is absorbed by ground state electrons to get to the excited state. So if that doesn't make any sense, it will be clarified in the diagram in the next slide. So let me just walk you through this really quick. This type of spectra is produced when white light is passed through a gas. The gas will absorb specific frequencies of light and allow the remainder of the light to hit a detector on the opposing side. The electrons in the gas atoms are excited from lower energy state to higher energy state. The energy radiation absorbed appears as dark lines in the absorption spectra produced. So different gases will absorb different frequencies of light. This provides each element with an atomic fingerprint. So if you look here, this is also hydrogen, okay? But at the bottom here, what you're seeing is the absorption spectrum of hydrogen. Notice that the lines are identical in placement as the lines in the absorption spectrum. What you're doing now is you're allowing the light to pass through the element, and that element, as it's absorbing the photons that it requires to jump to excited state, it's leaving those dark lines. So let's go to the next slide to see what this looks like. So this diagram here clearly shows how we accomplish these absorption spectrums. And so the canister of gas is going to be highlighted right here, okay? Now it's important to note that this canister of gas is cooled. The reason why we cool the gas before we run the experiment is because cooler gas is far more effective at absorbing energy than, of course, energized gas. And so we cool the gas before we pass white light through it. This is a continuous spectrum that we're passing through the gas. It is a spectrum that has the full rainbow. It is pure white light. And it's coming from a source that's producing that white light. It passes through the cool gas. And of course, the cool gas is going to absorb specific fragments of that white light. So specific photons from the white light will be absorbed by the electrons in this cool gas, and those electrons will jump from ground state to excited state. As they're jumping from ground state to excited state, the remainder of the light passes through the gas, through a slit, and hits a prism, okay? And the prism is going to split the remainder of the light that passes through that gas to a detector. On the detector, you'll see these distinct dark black lines. And those black lines represent the photons that were absorbed by the cool gas for its electrons to jump from ground state to excited state. And so if you look at the absorption spectrum of hydrogen and the emission spectrum of hydrogen, both of them have lines in the exact same regions. And the reason why this is because in the emission spectrum, you saw that those electrons, when they fell from excited state to ground state, they emitted these distinct colored lines. But in the absorption spectrum, what we tried to accomplish here is we wanted those electrons to absorb those specific colors, and we wanted the rest of the light to pass through, which gave us these dark lines. Okay, and so that's why we can use these spectrums as fingerprints or as identifiers for specific elements. What's important to note is that for absorption spectrum, it's very difficult to do an absorption spectrum for elements that do not exist in gaseous state or cannot be kept in gaseous state under pressurized conditions. The reason why is because we need to pass light through them. Okay, and so our main identifier really is the emission spectrum of many of these elements, okay? And this whole process, this whole analytical method is called spectroscopy. It's important to know that this whole concept, everything we've talked about so far in this lecture, is spectroscopy. That's the method that we're using here. That's the analytical method, okay? And so this finally brings us to our last concept of this lecture, the quantum. In 1900, a physicist named Max Planck, he's a very famous physicist, suggested that matter at the atomic level can absorb or emit only discrete quantities of energy. And you can see that with hydrogen. So hydrogen can only absorb and can only release specific amounts of energy. Hence the specific lines on its spectrums, okay? Each of these specific quantities are called quantums of energy. So if you look again at the hydrogen absorption spectrum, okay, each one of those black lines is a quantum of energy. It's a specific quantity of energy, hence quantum, okay? Each one of those lines represents a photon that has a specific amount of energy, a specific quantum of energy, and that quantum of energy is absorbed by the electron, which causes it to jump, leaving that black line. Each quantum of energy carried by a light particle called a photon discovered by Einstein. Albert Einstein was the man who discovered photons, and he was the one who named them. So, in other words, Planck said that the energy of an atom can be quantized. And the reason why this is true is because each element absorbs specific quantums of energy. Now, it doesn't absorb one specific quantum of energy, it absorbs quantums of energy. So look at hydrogen again. The hydrogen absorption spectrum, it absorbs 5 different quantums of energy because each particle of light is a quantum of energy. Do you understand? And so if one particle of light is absorbed, that's one quantum of energy. But each one of those quantums of energy leaves a specific black line. And so it brings us to our pinnacle definition here, okay? Quantum mechanics. What is quantum mechanics? Quantum mechanics is the study of the interaction of energy and matter at the atomic level. So it's a very, 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 very fancy branch of science, but its base definition is pretty simplistic. It is simply the study of the interaction of energy and matter at the atomic level. Trust me when I say it gets far more complicated than that, but for the purposes of this course, that's really all we need to know. That's all we need to understand. We need to understand the interplay, the interaction of energy and matter at an atomic level, and that'll be the focus for the coming lectures and the coming slides that you will be presented with. I hope you understood this package, and all the best.